Question. Use the principle of mathematical induction to prove that for all n belongs to positive integers. That is the following statement. Now we answer this question. This statement can be written as sigma r equals 1 to n. Here is r multiply r plus 2 bracket. This equals 6 multiply n plus 1 multiply 2 n plus 7. So this is just another form of the statement. Now, step 1. For n equals 1, the left-hand side equals sigma r equals 1 to 1. Here is r multiply r plus 2. So this equals 1 multiply 1 plus 2. This equals 3. Then the right hand side equals 6. Here n equals 1. So here is 1 multiply 1 plus 1 multiply 2 multiply 1 plus 7. So this equals 6, 2 multiply 9. And this equals 3. The left hand side equals right hand side. So the statement is true for n equals 1. The statement is true for n equals 1. Step 2. Assume the statement is true for n equals k. So assume this statement here is r equals 1 to k. Here is r multiply r plus 2. This equals 6k, k plus 1, 2k plus 7. So assume this statement is true. This statement exists. Then for n equals k plus 1, the left hand side equals r equals 1 to k plus 1 r plus 2. So this equals sigma r equals 1 to k. Here is r multiply r plus 2 plus 1r equals k plus 1. Here is k plus 1 multiply k plus 1 plus 2. Now because we assume this statement exists, then we can use this guy to replace this guy here. So this equals 6k plus 1 2k plus 7 plus here is k plus 1 multiply k plus 3. Then this equals 6k plus 1 2k plus 7. Now plus here, this is 6 over 6 multiply k plus 1. Here k plus 3. So we change this guy to this guy. Then this equals 6k plus 1. Now we multiply k with 2k plus 7. Here is 2k squared plus 7k. And here is 6. Here is k plus 1. We multiply 6 and k plus 3. Here is 6k plus 18. Then this equals 6k plus 1. We combine this guy with this guy. Then here is 2k squared plus 7k plus 6k plus 18. Then this equals, here is 6k plus 1. Here is 2k squared plus 13k plus 18. Now let's check the 2k squared plus 13k plus 18. So here 2 equals 1 multiply 2 and 18 equals 2 multiply 9. And we go this way. Here 1 multiply 9 plus 2 multiply 2 equals 13. And here this guy is also 13. So this guy 2k squared plus 13k plus 18, this equals k plus 2 multiply 2k plus 9. So this guy, we go here, equals 6k plus 1 multiply k plus 2 multiply 2k plus 9. And this guy can be rewritten as here equals 6 and here is k plus 1, then k plus 1 plus 1. Here is 2k plus 1 plus 7. And this is the left hand side. Left hand side equals this 1 and equals k plus 1. Then the right hand side equals just use k plus 1 to replace the n. So this is 6 here k plus 1 k plus 1 plus 1 2 k plus 1 plus 7. The left hand side equals right hand side So for n equals k plus 1, the left hand side still equals right hand side. So we show that the result is true for n equals 1. And we also show that if it is true for n equals k, it is also true. It is also true for n equals k plus 1. Now, therefore, the result is true for all n belongs to the positive integers by the principle of mathematical induction. So we can check the logic behind the principle of mathematical induction. We show that for n equals 1, the statement is true. And then we also show that assume the statement is true for n equals k, then it is true for n equals k plus 1. So if it is true for n equals 1, then it is true for n equals 2. If it is true for n equals 2, then it is true for n equals 3. And now we show that it is really true for n equals 1. Then it is really true for n equals 2. Because it is really true for n equals 2, then it is really true for n equals 3, and go on. In this way, we prove that the statement is true for all n belongs to positive integers.